Good morning, dear. Today we are going to discuss the chapter waves. The chapter begins with the idea of what is a wave. A wave is a disturbance that carries energy from one place to another without actual movement of matter. For example, a wave when it is produced from one point, for example, a sound wave produced from one point, it moves through the medium, that is, it moves through the air by disturbing the air particles or air molecules in it. It carries the energy from one place to another. So there is no actual movement of the matter. Matter will remain there itself. The particles present in the air will remain at the same place, even though they got a disturbance. That's what we say. Waves are disturbances that carries energy from one place to another without any actual movement of matter. There are different types of waves which we have studied. One is a transverse wave, other one is a longitudinal wave. Let's first consider transverse wave. You already know that, you have studied in 9th standard. Whenever a wave propagates, there is a particular direction of propagation and there are particles also inside. The particles may vibrate. Depending on how the particles vibrate, whether they vibrate along with the direction of the wave or perpendicular to the direction of wave, we classify waves into transverse and longitudinal. For example, if you take a stone and put it in a pond, a silent pond, if it is very steady without any disturbance, if a pond is there, you put a stone in that and you know that the waves will be from the center. From the center, wave will be propagating to the sides. You can see the waves will go up and down. That means the particles in that will move up and down. If this is the direction of this towards the right side, if the direction of the wave, particles may move up and down. That is called a transverse wave. This kind of waves we can produce even in strings. A stretched string, you can produce a wave like this. Even in a slinky, you can produce this kind of waves. So string wave, water wave, electromagnetic wave, etc. are transverse in nature. Electromagnetic wave means waves like light, heat, ultraviolet, X-ray, etc. Those waves or these radiations. Some situations, the waves will be formed and the wave will travel in a particular direction and the particles in the medium will vibrate in the same direction. For example, in the case of sound wave, sound waves are produced by vibration of air particles. So here are some air particles. If these are the air particles, and from here, if a wave is produced, a disturbance is produced, this will move this will try to move these particles in the direction of wave, so that particles here, air particles, will vibrate along with the direction of the wave. That kind of waves we call as a longitudinal wave. So the waves whose direction of propagation and the particle vibration are in same direction. Sound is a longitudinal wave, you already know that. And in spring or stretched string, we can produce longitudinal waves. Some of the terms related to a wave, the pictorial or graphical representation of a wave is like this. This is actually a representation of distance as well as the vibration of particles vibration. Here, suppose here is a particle. When a wave is produced, this particle can move upward It may reach to a height up to here. After that it will come down like a wave in a water. It will come again, it will go a little down and again go up. Now the vibrations in the positive direction, that means in the positive half or in the upward direction, that we can call as crest, and the vibration in the negative direction or a downward direction we call as a trough. The distance up to which a particle can move either upward or downward, maybe if it is up to here, this is known as the displacement of the wave. Displacement means at any time the distance up to which a particle moves, that is displacement. Now there is a maximum displacement, that is what you see here. This is the maximum displacement a particle can happen either in the upward direction or in the downward direction. This maximum displacement is known as the amplitude A. So if this is the maximum displacement, this is known as amplitude represented as capital A. The maximum displacement on either side. We represent this amplitude in meter. Suppose a wave starts from here and it goes to a height, the particle reaches the maximum height. It reaches the maximum height in the opposite direction, comes to the average or mean position. This is known as the mean position. This length from here to here, this length is known as wavelength. It will be also equal to the distance between two crest, or it can be equal to the distance between two trough also. This wavelength is also expressed in meter. Another one term is a time period. Time period means time taken by a wave to complete. That means the time taken for starting from here up to here. This is known as a time period represented as capital T. Time for one wave, that is capital T. There is another term called a frequency, which gives you the number of waves produced in 1 second. In 1 second, how many waves are produced? That is frequency. Frequency is expressed in a unit hertz. Time period, as usual, will be expressed in seconds. There is a term called a wave number, which is represented as a nu bar. Nu is the symbol for a frequency, a bar that shows wave number. This wave number is nothing but the reciprocal of wavelength. It's 1 by lambda. The reciprocal of wavelength is what? Wave number. And it's expressed in meter inverse. Another important term is angular wave number or propagation constant. That is represented by the letter K. You know, wavelength lambda, we have seen it is a distance between two crest or two trough. Here the ratio 2 pi by lambda, 2 pi by wavelength, that's known as angular wave number, or it is known as propagation constant, that is K, which is 2 pi by lambda, that is angular wave number or propagation constant. It will be expressed in radians per meter. Similarly, there is a term called angular velocity or angular frequency, and that is represented as omega, which this you have studied in chapter 3 already. You have seen it is the angular displacement per unit time, like our velocity displacement by time. Here angular displacement by unit time, or it can be even called as a rate of change of angular displacement. There is a d theta. If you represent d theta as the angle change, angular displacement, d theta by dt is what? Our angular velocity. It can also be written as 2 pi by t. It will be equal to 2 pi by t also, and its unit will be radians per second. So far we have discussed different terms. One is wavelength, what is the amplitude, what is displacement, what is frequency, time period, wave number, angular wave number, and angular velocity. Now, what we are going to do is we want to know how to express speed of a wave, especially a transverse wave. How do we express the speed of a transverse wave? Let's consider a stretched string. First one, let's consider a stretched string. A string that is stretched between 2 points. It is experimentally seen that the speed of a wave in a stretched string, a transverse wave produced in a stretched string, is v is equal to square root of t divided by m. When you make a stretched string, the string will have a mass. Even though it's very light, there will be a mass. And it will have a length. And that will be stretched between 2 points. That means with the help of a tension, we stretch the string. So here T stands for the tension you are applying on the string, and the small letter m is the mass per unit length of the string. That means mass coming in 1 centimeter unit length of the string, or it can be even 1 meter. Standard unit will be 1 meter. So mass per unit length is small letter m. That is a total mass of the mass per unit length, means how to calculate is total mass of the string divided by the length of the string. So this is the equation for the speed of a transverse wave in a stretched string. So the equation was suitable for speed of a transverse wave produced in a stretched string. Now these transverse waves can be produced even in solids, and if you take a solid material of density rho, and if its rigidity modulus is r, it's related to elasticity, then that rigidity modulus is related to its elastic behavior. So speed of transverse wave in solid depends on two things. One is the density of the medium and the elastic nature of the medium. That is square root of r by rho. Now let's consider some longitudinal waves. For example, a longitudinal wave produced in a fluid medium. For example, air or water, any fluid. It depends on the flow. The speed depends on two factors. One is the density of the fluid. Other one it is dependent on the bulk modulus of the fluid. That's again dependent on the elastic behavior of the medium. So longitudinal wave in fluid speed is root of b by rho. B is the bulk modulus, rho is the density. Similarly, in solids, these longitudinal waves in solids, their speed depends on three factors. One is the bulk modulus, also on the rigidity modulus, and the density of the solid medium. It is calculated as square root of b plus 4 by 3 r by rho. If it is a solid rod, a particular solid rod, you can produce a wave in a rod also. A solid rod you take, that rod will have a modulus of elasticity, that is Young's modulus, and that rod will have a density rho. So the speed depends on these two factors. One is the Young's modulus, other one is the density, square root of y by rho. Now let us consider the particular longitudinal wave, that is a sound. So here let's first consider the speed of sound in gas or air. That is, we know that sound is a longitudinal wave, and we can calculate the speed also. Already we have seen that the speed of a longitudinal wave in a fluid medium is root b by rho, that is bulk modulus by density. Now, Newton came with an idea that this bulk modulus is a little difficult term. Instead of bulk modulus, can you replace it with something else? That is what Newton has tried to look after. Now, what he did is, for that he made some assumptions. First one is, sound waves travels in a gaseous medium as compressions and rarefactions. It does not change the temperature of the medium. While it is traveling, it does not change the temperature of the medium. This is one idea he proposed. He said sound is a longitudinal wave and it is produced as compressions and rarefactions. And while these kind of waves travel, there is no change in the temperature of the medium. This is what he said. And he called this process as an isothermal process, where the temperature is not changing. He told it's an isothermal process. Already for an isothermal process, for a gaseous system from Boyle's law, we have a relation that is P into V is a constant. You might have studied in chemistry, PV is a constant. The equation for that comes with the idea PV is equal to the ideal gas equation. PV is equal to nRT, where N is the number of moles present in the medium, R is the gas constant, and T is the temperature. What Newton said is, if the medium the process is isothermal, temperature is a constant, which means T is constant, R is constant, and N is also constant. As per that, PV should be a constant. This is what he said. Now what he did is just this equation, if PV is a constant, let's differentiate this. PV, two terms are there. So PV is a constant, that's what he said. He just differentiated it. He took the derivative of that. D of PV is a D of constant. That's what he did. D actually shows the change, and D of a constant means 0. There is no change in that. D of PV, how we have to first find is, this is a particular rule, that is D of UV in mathematics. U and V are two terms. That as per the rule, it says this is equal to U into dV plus V into du. That is first quantity into change in the second quantity plus second quantity into change in the first quantity. As per that, PV, if you take P into change in volume, pressure into change in volume, plus volume into change in pressure, that is equal to 0. That is P dV is equal to minus V dP. I can take this term to the right side. Then you get the P is equal to V dP by dV. Now this I will make a little modification, that is dP. This term dV and V, we take V to the denominator, dV by V I can write. But dV by V is change in volume by original volume. This is the volume strain, change in volume by original volume, that is a volume strain. Pressure is here, change in pressure by volume strain, that gives the bulk modulus. So what Newton understood is, if you consider this process as an isothermal process, the pressure and bulk modulus are equal. So the previous equation, we had the previous equation, that is root B by rho. In this, as per Newton, B is not needed, bulk modulus is not needed, but you can replace it with the pressure of the medium P. That's what he said. Then with that, he just made an equation, V is equal to root P by rho. What he did is, he substituted the value of pressure as atmospheric pressure and density of air 1.293 kilogram per meter cube. Then he got the speed of sound in air at standard temperature and pressure as 280 meter per second. 280 meter per second. But that value was not exactly correct, because it was somewhat near to the value. It was lesser by a little, the actual value experimentally was found to be 331 meter per second. So his formula was not accepted. So his assumption that the sound travels as longitudinal wave with compressions and rarefactions without changing the temperature was wrong. It was not 100% correct. So another scientist came named Laplace. He corrected this formula. He said there is a little correction needed in this. That's what we are going to see in the next video.